Here the components of a modern computer is shown. We have one or more processors, main memory, disks, printers, keyboard, mouse, display, network interfaces, I/O devices. Here there is a main board of a computer, and in this schema the components are written. We have a central processor socket, and there a processor is to be inserted. We have memory slots where memory boards are to be inserted. Here we have integrated circuits for the memory. We have drive connectors, BIOS processor, input-output I/O, computer case connectors, battery of the main board, integrated audio chip, PCI slots here, AGP graphics slot there, and PS2 network parallel serial and USB connectors for the main board. If you consider a computer system, at the bottom we have hardware, and on top of it we have operating system in the kernel mode, and then user interface program, which is a interface between the user programs and the operating system, while the operating system is an interface between the user interface part and the hardware. In the user mode, we may have web browser, email reader, music player, word processors, etc. Operating system uses kernel mode of the microprocessor, whereas other programs use user mode. The difference is that all hardware instructions are valid in kernel mode, where some of them cannot be used in the user mode. A user can change his program or write his own program piece if he is not satisfied. A user cannot change, for example, the clock interrupt handler, which is part of operating system and is protected by the hardware against attempts by users to modify it. Note that embedded systems or interpreted systems might not have a kernel mode. To perform addition in a system where there is no operating system installed, we may need to consider memory locations and hardware knowledge of the underlying system as follows. Assuming that you have Motorola MC6811 or any other similar computer hardware knowledge. LDAA address 80. Loading register A, the number at memory location 80. LDAB address 81. Loading register B, the number at memory location 81. ADDB, adding these two numbers given here. STAA address 55, storing the sum in register A to memory location 55. The above program segment would not work for an 8086 machine, but if we have an intermediate layer, our programs may obtain some advantage of mobility by not dealing with the hardware. For example, C is equal to A plus B. This syntax may be suitable for both processors. Another example, we have disk drive hardware, and on top of it we have disk driver and files. The files may be loaded disk drive hardware by using the software disk driver without knowledge where this drive is connected. We prefer to be able to write a simple program segment with no hardware constraint. Through the operating system, a more sophisticated program segment with hardware constraint is used to convert this code into the machine language, and when it is loaded in the hardware, we can get what is the hardware response for that code. In a computer, we have hardware, and for that hardware, whatever the used processor, we have a related machine language to write program for that processor. And this is the machine part. However, by the use of the operating system, we have virtual extended machine. So if we are using operating system, it is on top of the machine language, so it is extending the machine to virtual machine. Operating systems turn ugly hardware into beautiful abstractions. We have hardware for which it is hard to write codes, and operating system is written by considering the properties of the hardware, and it provides a beautiful interface for writing the application programs. So the programmer who is writing application programs does not need to know what are the details of the hardware. If we consider the hierarchy in a computer, at the bottom we have hardware, as we mentioned previously, then machine language, and then operating system. And above them we have system programs, which is calling the operating system, and then application programs are written on top of it. So application programs uses the system programs, which is an interface for the operating system, and it is an interface for the hardware through the machine language. When we consider operating system as a resource manager, in top-down view, operating system provides abstractions to application programs. For the bottom-up view, operating system manages pieces of complex system, and in alternative view, the operating system provides orderly, controlled allocation of resources. An operating system keeps track of which programs are using which resource, grants resource requests, account for usage, and mediates conflicting requests from different programs and users. Resource management includes multiplexing, that is sharing, resources in time and in space. Now we are going to consider the history of operating systems. In the first generation of computers, which is between 1945 and 55, vacuum tubes are used. In the second generation, which is between 1955 and 65, transistors and batch systems are used. In the third generation, between 1965 and 1980, we see integrated circuits and multiprogramming. In the fourth generation, which is from 1980 to present, we have personal computers. And for the fifth generation, which is from 1990 to present, we have mobile computers. As the first generation computing, we can consider Analytical Engine as the first computer. It is designed in 1840s by Charles Babbage, but could not be constructed by him. An earlier and simpler version is constructed in 2002 in London. You can visit Analytical Engine in Science Museum in London. The first electronic computer is ENIAC. The abbreviation ENIAC stands for electronic numerical integrator and computer. It is built in the 1940s, weighted 30 tons, 2.5 meters high and 1 meter deep and 30 meters long. It contained over 18,000 vacuum tubes that were cooled by 80 air blowers. Notice that there is no memory to store the code. Instead of that, each instruction is inputted to the computer through different combination of connections. A connection is constructed and then it is inputted to the computer. It executes that line and then another connection is established for the next instruction. This is the back side of the ENIAC. We have vacuum tubes. Vacuum tubes are used in computers before transistors are developed. Programs were loaded into memory manually using switches, punched cards, or paper tapes. Here another picture of coding of ENIAC by cable connections. This is a punch card. We have combination of holes in each column and these combinations are corresponding to a symbol. For example, here through these combinations of the holes, here free punch cards is written. We have 80 columns for each card. So if you are going to write programs in those days, then you have to prepare a punch card for each line in your code. This is the punch machine. You insert the cards from here, then you write the line and it is punched on the card. Another way to input programs to the computer is to use punched paper tape and it is 25 mm wide. We have ASCII 7-bit character code, even parity. Here the bits are ordered as bit 1, bit 2, bit 3 and sprocked holes in order to able to turn the paper. Then we have bit 4, 5, 6 and 7 and this is for the parity bit. If the number of bits here is odd, then we have one more hole here to make the parity even. Here we have the ASCII codes for the letters. This is corresponding to A. That means that 1, 0, 0, 0, 0, 0, 1. And parity is 0. And letter B is here. This time we have 0 for bit 1. Then bit 2 is 1, etc. And here all the letters in ASCII is written from A up to Z. And the paper goes in this direction. So this is the first letter as the input, then this is the second, and so on. In the first computers, when the transistors are started to be used, there were early batch systems. In the early batch systems, a programmer prepares the punch cards and then brings those cards into the computer center, and there is an input-output device, here numbered as 1401, in which we have card reader, and through that card reader, information on the cards are read, and those information are recorded on the tape using the tape drive. And then the operator carries input tape to the computer, and this machine 7094 does computing, gets the input from the tape, and whatever the output is recorded on another tape. The operator carries output tape to output device 1401. This is the output device to get information from the tape and to print the output through the printer. Fortran is one of the earliest programming languages. The structure of a typical Fortran job is given here. The first line is describing who is the programmer. Then there is a part corresponding to the program. It starts with the instruction, say that this is the beginning of the Fortran program. And when it finishes here in the cards, there is a load statement to load the code into the computer, and then run statement to execute the code. And here we have the data for the program, and this is showing the end of the job. The characteristics of the third generation computers are integrated circuits used in the computer hardware and multi-programming provided by the operating system. Finally, the idea of multi-programming came. Multi-programming means sharing of resources between more than one process. By multi-programming, the CPU time is not wasted because while one process moves on some input-output work, the operating system picks another process to execute till the current one passes to input-output operation. Here an example of a multi-programming system with 3 jobs in memory. In the area of the memory having the lowest address, we have operating system, and the jobs, job 1, job 2, and job 3 are loaded into fixed partitions in the memory. These are the partitions for the jobs and for the operating system. With the development of interactive computation in 1970s, time-sharing systems emerged. In these systems, multiple users have terminals. These are not computers. Terminals are connected to the main computer and execute their tasks in the main computer. Here we have the main computer having a CPU executing processes by utilization of the operating system, for example, Unix operating system, and these are the terminals. Terminals are connected to the main computer and used for input and output. No processing is made in the terminals. They do not have central processing units. In the third generation operating systems, the computing is considered as a utility like electricity. EE442 is the mainframe, and Multics is the operating system. It is short for Multiplexed Information and Computing. It stands for Multiplexed Information and Computing Service. Multics had a huge influence on subsequent operating systems, especially Unix and its derivatives, FreeBSD, Linux, iOS, and Android. A stripped-down one-user version of Multics led to Unix. 2 major Unix versions followed it. One is the System 5 from AT&T, and the other one is BSD from the University of California at Berkeley. To make it possible to write programs that could run on any Unix system, IEEE developed a standard for Unix called POSIX that defines a minimal system call interface. In the fourth generation, we have mini computers, and then it is evolved to microcomputers. That is, the personal computers that we know. Intel 8080 is the first general-purpose 8-bit central processing unit. The first disk-based operating system, named CPM, emerged. This is short for Control Program for Microcomputers. IBM entered the PC market. The disk operating system DOS is developed by Bill Gates, and MS-DOS, which is Microsoft Disk Operating System, is developed. Apple entered to the PC market. The operating system is called Mac OS. And we have Mac OS X, for example. This is based on Unix and also graphic unit interface. Microsoft developed Windows, Windows 95, Windows 98, Windows NT, Windows 2000, Windows XP, Windows 2007, etc. These are graphic unit based. The other major contender in the PC world is Unix and its derivatives such as FreeBSD. X-Window, X11 has basic window functions. GNOME or KDE, it has a complete graphic unit interface running on top of X11. Minix is a small Unix clone for the education purposes, and Linux is free production version of Minix. The network of computers are generated, and use of the networks required network operating systems. In network systems, each process runs its own machine, but the operating system have access to other machines. By this way, file sharing, messaging, etc. become possible. In networks, users are not aware of the fact that they are working in a network. However, when information is to be exchanged, the user explicitly handles the transfer of information. This is a network of computers. Each is a computer having its own CPU, RAM, etc. An operating system supporting networks is installed on each of them. Distributed systems are similar to networks. However, in such systems, there is no need to exchange information explicitly. It is handled by the operating system itself whenever necessary. A distributed operating system is one that appears to its users as a traditional uniprocessor system, even though it is actually composed of multiple processors. The users are not aware where their programs are being run or where their files are located. That should all be handled automatically and efficiently by the operating system. If we consider fifth generation operating systems, we have a mobile phone on which a personal digital assistant is working. This is called a smartphone. Symbian operating system used in the earlier models of Samsung, Sony Ericsson, Motorola, and Nokia. RIM's BlackBerry operating system introduced in 2002. Apple's iOS, this is released in 2007. Nokia phone uses Windows and Google's Android, a Linux-based operating system. This is open source and available under a permissive license. This is used by a huge community of the developers.